Okay. Okay. Yeah. Can you try now, Prof. Fox? Yeah.
Yes.
Okay. Yeah, we are seeing the screen.
All right. So I will just talk about, this is a slide deck which Arup has access to and anybody can get. And I will just go through it briefly to tell you the essential points. So the main reason I look at systems like Cylon is to try to support computing for scientific and engineering research. And I edited a book recently with around 40 chapters, which goes through lots of areas of science, astronomy, experimental physics, material science, drug discovery, general bioinformatics, lots of earth science and environmental science and climate and weather, study of power grids and fusion. And of course, there's also social science of studying social media, and all of those systems are being transformed by the same technology that is giving you ChatGPT and the other AI commercial applications, which are usually in vision or large language systems. So we're aiming to try to understand how to process large amounts of data. So let's just have a few remarks about computing. So just over the last 10 years or even more recent, continuing recently, there's been a huge increase in the amount of computing time used by the world. I read an article recently which says the total amount of computing had actually over the last 3 years or something had gone up a factor of 4. If you'd added up all the supercomputers, all the cloud computers, the total computing power was 4 times bigger than it used to be. And that is almost entirely driven by so-called deep learning, which is a revolution in the way we can analyze data to use AI on it. And this plot here shows the total computing power measured in floating point operations per second against time. And this stops in 22. It continues to increase. And here's another such plot with which actually shows that at least for some systems, they understand how they scale as a function of there are 2 numbers which count: the number of tokens, that's the amount of data, and the number of parameters, that's the size of the AI model that you're building. And I went to a meeting recently where they were aiming to train 30 trillion tokens, and maybe 1 trillion or so parameters to try to build a model to describe large amounts of science. So these numbers are huge. And because the amount of computing is so large, it's very important to try to understand how to efficiently process them, because you can't afford to throw away computer power. It's very bad for the environment because it uses up a lot of energy, and it also will stop you from competing with other people. So here, this points out that the amount of money spent on computing is, well, at this time, this largest one here, which is actually quite small today, cost almost $7 million to train the model. So, and that's just the training. In this was maybe a year ago. They said that if you use ChatGPT widely in inference and in searches, that would cost you $100 billion. It would actually cost Google or Microsoft, OpenAI, $100 billion a year just to support the inference. Always with deep learning, you have the training cost, which is a one-time cost, and then every time you use it, each of those costs is smaller, but there are a lot of them because lots of people are using them. That is actually a little different from science. In science, you do more. The number of inferences is less than the amount of the training can be as big or bigger than industry, but the inference is smaller because for commercial application, the number of inferences is multiplied by the number of people. Whereas in science, you might multiply it by the number of scientists in the field, and that's a huge difference in size, much, much smaller. All right, well, I don't think I need to go through this. So we're looking at this system to support deep learning. And typically you might have a user interface, which will be a Jupyter Notebook, a system that many people use is called Google Colab. That is effectively a Jupyter Notebook, and it supports software running on well, in that case, a Google Cloud, but in general, it's a cloud or a machine like Grafana or the computer science cluster. And if you look at what happens, you start off with some data on the left. You process the data, which means you put it into standard form and you convert into so-called tensors, and then you either train it or you inference it. Then then you look at the results and maybe you produce a nice visualization, or else you store the data somewhere, or you convert it into speech and tell people the answers and things like that. So when you look at this pipeline, in here we have things like TensorFlow and PyTorch. And here we have things like Apache Spark and Pandas, the Python processing system. And here again, afterwards, you have the same types of processing. And there has again here been a change. It used to be that the data engineering cost more time than the actual training. Nowadays, training is probably 10 times larger than the data engineering. That's because deep learning is computationally much more intense. So I've been working on this problem for some time, and when we started, we used Java-like systems like Spark, or we had versions of Spark we built ourselves called Twister, and those used to be dominant, and Spark is still used, but it's actually not nearly as easy to use as it used to be, because the system in the middle is actually written typically in Python and C++. And Spark originally used to be written in Java, as was our own systems. They're always written in Java. And it is not terribly efficient to link Java to C++. And also Java is not as high performance. Java doesn't perform as well as C++. So a lot of the data engineering systems are now written in C++, and Cylon is written in C++. So Cylon is effectively a data engineering system. Its characteristic is that it effectively prepares the data by speeding up the Python processing, like Pandas. And it can also interface with other things like SQL engines and stuff like that. And it can link to Java or C++, but it itself is written in C++. and its most efficient implementations will use those languages. A key feature of it, and this is another view of the same thing, showing this pipeline where you start off with the data engineering and end up with the deep learning. And we said we need to, one of the things we want to do with Cylon is integrate it better with the deep learning. At the moment, we focus mainly on the data engineering steps, the Python Pandas steps. And so you probably, I gather you probably haven't had parallel computing classes, but all of these, every single one of these systems, deep learning, Cylon, when you have large data, you have to run, use parallel computing, which means you use lots of computers to process, to do the operation, and run them all together. And I used to give classes on parallel computing, and I used to explain it by using an analogy with say building a wall. When you have building a wall, you might divide the wall up into different parts, and each person, and then you have several bricklayers who are building the wall. They would each build part of the wall. Now that's never going to work well unless the workers coordinate at the places where the parts they're building link up. And the same is true in parallel computing with computers. You need the overheads correspond to the so-called synchronization, the linking of the computers to, when they exchange information, so that the parts that you divide the problem up into parts, you process each part separately, but then the hard problem is linking it all together. And that has to be done very efficiently. And Cylon, we know how to do that, and Cylon has implemented that. And essentially, we do not want the user to have to run in parallel. The Cylon provides operations like sort or join, which have already been written in parallel. And if you look at all those operations, there are lots of them in Pandas, which has data frames. There are 224 different Pandas operators. And on principle, you need to write parallel versions for all of them. We've written parallel versions for about 30 to 40 of the most important. NumPy, which is a standard Python array manipulation system, it actually it is written to run in parallel and to run efficiently. One technology that's very important in this regard is called Arrow. That's an Apache project, and it is a way of dealing with arrays efficiently. And Arrow stores array efficiently. Notice even TensorFlow and PyTorch, they have lots of operators. Every layer has an operator. Every shuffle is an operator. There's lots of all of these current systems can be thought of as a set of operators which you compose when you write a deep learning code or a machine learning code. You join the operators together which is, say, for the largest computer vision deep learning systems, they may have 200 different layers, so that's a lot of different operators, and then the overall environment joins them together. Joining them together is called workflow, and one of the things Arup is doing is trying to link Cylon, which is effectively the system for running each operator, joining those operators together. And Cylon is essentially a very fast manipulator of tables, because if you look at these pandas, a data frame is essentially the same thing as a table. And so we're trying to make Cylon link well to existing systems, such as the workflow engine, which is Radical Pilot, operating systems where Dask is a well-known Python operating system. And here are these different operators, and there's some comments about how you parallelize them, which is probably not so important for you. But my PhD students over the last few years have looked at these different operators and parallelize them efficiently. And here is, then we then get a set of results when we try to test how well this performs. Here are various pandas operators like join and this has the number of computers that you use together. That's the parallelism, which goes up to 256 here. And here is the time. And you can see the time decreases as you increase the number of computers. That says the parallel computing is done well. You see it doesn't work so well at 256 separate computers. That just says that at that time, this overhead, which I mentioned, you had to minimize, of making the synchronization cost has got too large. And you can see somewhere in some of these operators at 512, it's actually running slower than 256. That just says the computers are getting in each other's way. I used to, there's a famous term in English called too many cooks spoil the broth. If you're trying to build soup broth, then if you have several people, you can actually chop up the onions or peel the carrots in parallel. But if you have too many of them, they can't all pour the results into the saucepan at the same time. So there is a maximum number of people who can work on building soup in parallel. And the same is true with computers. So these are just a variety of different operators and various technologies. GLUE is MPI and UCX are different synchronization technologies which we use. And here's the two types of curves, one called strong scaling, where you fix the problem and increase the number of computers. The other is called weak scaling, which is where you scale up the problem, you make the problem bigger as you increase the number of computers. These results we've shown so far are all strong scaling. And the largest time systems we've run are up to 10,000 computers on a big supercomputer at the Department of Energy lab at Oak Ridge, Tennessee. And here are this time, and again, you see actually here, this time increases at around 2,500 processors. If you make the problem bigger, just as if you have a bigger saucepan, you can put more cooks around it. If you have a bigger problem, you can use more computers, and this one continues to decrease up to 10,000 computers. If you make the problem, if you have a table with 50 billion rows. I pointed out that the number of parameters and data points and number of parameter models, they're measured in the tens of billions or more larger, hundreds of billions. So these large numbers are what you need to deal with. And so that's why these numbers here with large parallelism are relevant. And this is, I think, my last slide. And it shows that this is what Arab has been doing recently, which is trying to link Cylon to a workflow engine, because the workflow engine can then link between the different operators that Cylon is joining together. Well, Cylon is operating on individual operators. You have multiple instances of Cylon, and you try to join them together because you want to run the data set in a pipeline through a set of operators as you get more and more, you make more and more sophisticated total operators. All right, I'll stop there. Thank you. So what we need to do is to improve Cylon and also to link Cylon with PyTorch and TensorFlow, the major deep learning systems. Arab, do you want to take over now?
Yeah, sure. Thank you, Professor Fox. That is basically a brief overview of our project, that what we are trying to do here. But there are a lot of different parts of this project. Like as there are some parts where a student will work on the deep learning, machine learning part. Some student might work on the infrastructure part, where you guys can develop the pipelining and the process management, this kind of stuff. You know, there are also some other stuff where you guys can handle the communication layer part, where there are different communication frameworks like, you know, MPI, UCX, Glue, NCCL. We didn't support yet that. And also there will be some parts where, you know, there will be a support of different you know, data sets. Okay, so there will be different projects. The plan is we will have different team. Each member probably will have, like, you know, each team probably will have 3 members. And the plan is the same sentence I probably discussed with you when, you know, when I had a one-to-one session with you guys, right? So the idea is, like, you know, every team will work together closely, and we'll have a single weekly meeting. I will try to, you know, schedule that meeting in person, probably at Rice Hall, or, you know, if somebody unable to join, he or she can join via Zoom. So that is also quite okay. But each team member basically work together, discuss it, probably set a specific time, like, as you guys will, like, you know, you will spend some time, probably 10 hours per week. So you guys have to, you know, make it specific time so that you can, like, you know, work together, discuss together, share your problem if you face anything. And obviously we'll have a common channel, like probably in the Discord, or probably we'll use Discord because it's free. And and share all our ideas and solutions. And if you guys face any problem, you can definitely, you know, put different questions there so that other people can answer it. And along with that, we already have a portal where I will upload all the training materials, discussion points. Even this video will be uploaded to that portal. Probably we will create a YouTube channel and just to post all of our training materials, discussion materials there. The main goal is to create a strong, you know, research team, and this project should get big exposure so that other people can use it. The primary focus to, you know, create the Cylon more, you know, to implement many features and release a standalone library so that other people can use it. Then we have different plans, like, you know, adding features, like, you know, machine learning compatibility for distributed training, inferencing. Then we probably add different inbuilt model support that the other guys normally use during the research. Probably people from different domain, like let's say if one water and environmental science student from water and environmental science wants to do something with machine learning and deep learning, he can use it. So all of this stuff, the plan is to basically release a standalone Cylon library with a lot of different features, and we will have we will have separate discussions about the planning and features, obviously. So we have 3 minutes. Professor Fox will leave. I'm not sure, is Professor Fox still here? Oh, yeah, Professor Fox already left. So let's go one by one. At first, you guys will introduce yourself along with, like, what is your strong point and what you are expecting from this research project. Okay, so let's start with Lucas. Lucas, are you there? Hello.
Yes. Hello.
Hey.
Hey. Okay. So I like by strong point, like our languages that we're strong in, or just like general stuff?
Okay, so Python, you told that you're pretty good at Python, right?
Yeah.
Writing code.
Okay.
Okay, so yeah, obviously the strong point, and which year you are currently in, and what is your major?
Okay.
These three information.
Yeah. All right. I'm a second year. I'm majoring in computer science and applied statistics. Yeah, I'm pretty strong with Python. And then out of this, I'm kind of looking just to gain experience with research overall, but also just kind of see how I enjoy this kind of branch of computer science relating to like more data oriented stuff.
Perfect. Thank you, Lucas. So, Arup.
Hi, my name's also Arup, but I guess for clarity, you can just call me Arupava. I think that would make it a little bit easier. But yeah, I'm a third year. I'm a computer science major in the engineering school. I would say definitely my strong suits are, I mean, I've like used Python before and I've used like a lot of different like languages for my classes, but I definitely like I feel like my biggest strong suit is I can kind of just like get put into like a problem where I have to like use whatever technology, whatever system I have to like be like dealing with, and I'll just be able to like typically I've been able to like figure it out through like I mean it might take a long time, but I usually figure things out. And then what I want to get out of this is I definitely like want to get, like I said, like Lucas does, I definitely want to get like a experience working in like a research team. I'm also really excited like after this presentation like to learn that like we're like really making like essentially we're trying to make like a product for outside like outside end users to use, and I think that's really exciting too. And also like getting that experience making like a system that deals with like a lot of data, I think that's also a really exciting like experience. And was there anything else you wanted me to add?
Yeah, that's perfect. Yes.
Okay.
Okay. Next is Colin. Colin, are you there?
Hi, everyone.
Colin.
I'm Colin. I'm a second year majoring in CS and minoring in data science. My strong point is definitely Python and NumPy, specifically with like machine learning processes and things like that. Um, I'm really excited to, get to learn new technologies, especially, most of us are going to be STEM professionals, and that's going to be a huge part of, all of our lives, just being just constantly learning. And I feel like getting that experience in this research team and working with others is going to be something I'm really looking forward to. And also, I'm on the Geminis, if that's how you pronounce it, the Geminis team, and they're focusing on like ML, IR, Aero, and that's something completely new to me, but I'm really looking forward to learning more about it.
Cool. Yeah, that's name. Those are basically Greek philosopher or architect or something. I was trying to kind of align some kind of what part of the responsibilities, what part of the projects you guys will work on, and how your responsibility align with some kind of philosophical point of view. But anyway, so that's really fine. And those team is not fixed yet. I just put your name into different team, and it's quite okay. You guys can interchange teams, and probably we probably have you know more team if the requirements of, of of any features requires that, or to have separate team, probably two members specific to work on, let's say, developing MLIR on. MLIR basically means multi-level intermediate representation, some kind of optimization into the compiler layer. When you execute any instruction, there should be a optimization into the compiler layer, and that intermediate representation basically translate the request that you are sending from the top level and basically translate to the instruction that LLVM. LLVM is, you probably heard about that. LLVM basically the underlying and intermediate representation for the compiler. So that part, we do have some projects and we do have some ideas. So, some of you guys probably, and if you guys are interested, so it's very important to have the interested. So I'm not something like that. I'm not someone like, I put you into one team, one project, and you don't feel passionate about that, and if you don't feel excited, then it will not gonna work. Research normally doesn't work like that. You should have passions. You should have excited. You should be excited like to learn new stuff. So that's how we'll give you motivations to implement stuff. But anyway, so okay, carry on, Colin. Yeah, I'm okay. You guys can carry on. Yeah, it's fine.
I'm done introducing myself.
Okay, perfect. So next is Shreya, right? Am I pronouncing correctly?
Yeah, I'm
Okay,
Shreya.
okay, Shreya.
I'm a first year at UVA in the School of Engineering and Applied Sciences, and I'd say my strong points are in terms of languages, Python, but then in terms of interpersonal skills, it would be being able to kind of come up with like some sort of like broad solution to a problem. Like it might not be like a direct like coded solution, but I feel like I can logically think through a problem, which I feel like has been really helpful. In terms of what I'm looking forward to, since I'm only a first year, I would hope that this experience kind of lets me understand what specific types of computer science I'm really into, so that in my third and fourth years, when I'm taking specific computer science elective classes, I can kind of gauge my interest based on this experience.
Perfect. Yeah, next is Alex Young.
Hi, I'm Alex. I'm also a first year computer science student within the School of Engineering. I am pretty strong with Python, and I'd say I'm pretty detail oriented, and I like working in teams, especially in coding with like GitHub and version control. I'd say I'm really looking forward to working with data outside of class, because currently I have to take some of the lower level classes, and I also look forward to, like Arup was saying, building an actual project that will go to end users.
Okay, thank you. So next is Alex, right? Alex Fateh. Am I pronouncing correctly?
Fateh. Close
Oh,
enough.
Fateh. Okay, sorry.
No problem. Yeah,
Yeah.
so I'm Alex. I'm a third year CS major in the E school. Kind of like everyone else, my strong suits pretty much align good with Python. Over the past year, I've been working on another project in the Biocomplexity Institute, specifically in machine learning. And kind of something I want to get out of this project is to dive a little bit more into parallel systems and kind of get some experience in that department.
Okay. Thank you, Alex. And next is Asad. Asad, are you listening? Hello. Okay, your mic is broken. Okay, and so let's move on to Aaron. Aaron, are you there?
Yeah, I'm a second year CS and econ major. I would say my strengths are mainly in Java and Python, and I'm mainly looking to like gain some research, especially in like a field like high computing, and like I'm looking to gain more experience and learn more about just like data and like research in general.
Okay, perfect. So yeah, Asad just sent a message into the tune about him, so you guys can yeah, you guys can check it out. Okay. So the next plan is we will have a meeting every week, like next Friday. And my plan is to share you the probably all the training materials. So I have designed different stuff that are needed for this project. So what I will do is basically probably I and there are 2 other PhD students working at the Prof Box. So we will give talks about different topics. From basically we will start from the basic, as some of you guys are first year, second year, there are a lot of different stuffs you probably don't have any idea. So this is totally fine. That's why we are here. We will learn together, share our ideas. If someone knows something, he or she can share to others. So that's totally fine. So that is my plan. So Friday 4 p.m. Can we set this? Can you set this time, like every week at Friday 4 p.m.? Are you guys okay?
Alright.
Okay, perfect. Yeah. So let's set we will meet Friday at 4 p.m. So in the meantime, what definitely I will send mails, and all the communications will be on mail and in Discord channel. So I'll create a Discord channel or a group as well. And okay, Alex Fatayas, you work probably you work with Professor Fox, or you work in biocomplexity last summer, right?
Yeah, over the past year with Professor Swarup.
Okay, perfect. So do you guys is anyone have any idea how to run Python or C++ by using Slurm script?
Yeah.
Alex, yeah, that's why I was like asking you directly, because as you already work in the biocomplexity.
Yeah.
So you probably have this idea. So so I will basically add you as a trainer for describing how Slurm script works, and probably write a sample program by using Slurm. Okay, to basically run a simple program by using Slurm script.
Okay.
Okay.
I haven't used it on the cluster. I've only used it on Ravana.
Rivana is a cluster. Rivana is a supercomputer, and Rivana is a cluster. So
Ah,
we do have we do have CS cluster, and CS cluster is also supports Slurm, so that's also fine. So what you can do is access to your account and create a sample program and see how it works. Okay. Perfect. Okay, so that's all from my side. So I will after this meeting, I will send a bunch of emails to you for the next action item. Okay, and and obviously me, Alex, we already fixed our topic. Like we will give some kind of presentation or session about like parallel computing. Alex will give about Slurm. So what I will do is I will assign some of the topic every one of you guys to every one of you guys, so that you can read about that and probably give your presentations. Then we'll do some kind of exercise with a simple program, like how the parallel computing works, how distributed data frame works, and how we use those stuff into machine learning. Some of you guys have experience, like Asad has experience for handling machine learning, training, or data pipelining, right? So I should probably give presentation about that. Then I will give the introduction, in-depth introductions about the Cylon projects, and I will give access to our GitHub repository, source code, and you guys will build the Cylon projects and playing out. So that's the immediate plan. And obviously, based on our progress and based on our results, how we are doing, and also idea generations, then we will think about, like, what are the stuff we will do, or then we will ultimately target, like, what idea we'll publish, what we will do for the releasing of the binary, and how we can release our binaries, and how we can conduct all the documentation, this kind of stuff. We'll decide it later. So that's all from my side. If you guys have any questions for me. Okay, so thank you guys for joining this call. So let's end to this meeting. Okay, and talk to you on next Friday, I guess. Yeah. Okay, perfect.
Thank you.
Okay,
Thanks.
bye.
Thank
Thank
you.
you.
You have a great weekend.
Bye.